Ansys Fluent theoretically. Okay. So, now one of the TAs will show you step by step how to do that, and we will be doing in a straight pipe. Okay. So, the pipe flow, I told you the Reynolds number, and that Reynolds number should be satisfied before we do any kind of simulation. If it is laminar, we have to choose the laminar model. If it is turbulent, we have to choose the turbulent model. So, the TA will tell you what kind of Reynolds number he used, what is that Reynolds number value, and then he will show step by step starting from beginning. I think we already have our geometry, right? Geometry and meshing, and he will show you, or you will create the geometry here. Good. Okay. So, he will create the geometry starting from the geometry and meshing, the boundary conditions, and then the solution. But what he will do is he will use very coarse mesh, so that we can get very quick solution. Otherwise, it will take long time for the solution, and then we won't get any time. So, this is only for the demonstration purpose, but if you, when you do the real simulation, you have to use you have to do the mesh dependent test. Okay. So, I think I should welcome him to start it. If you don't have the Ansys in your laptop, or if you don't have laptop, you can share with someone who already has it. Why it is not showing?
That is only I am trying to figure out.
I think there is a quick comment there. Can you right click and see whether you can add anything here? Expand it. Already expanded. I think you can copy this one, make a copy, and delete the data from the copy. No, that one. Copy this one.
Yeah, that is I am copying.
don't copy the whole things. Copy, cancel it. Is it this one? Yes. Copy here. Yeah, right click and make a copy.
Okay. Okay.
Can I copy? Yeah. No?
Now I'm just saving it.
No, then we can do side by side and then we can delete.
Yes. Yes. So
Okay, you can just delete the data and we can start. Yes, sometimes it will hard to see. You open it? Who open the organs? Can you see the page here? Did you install it? So it is taking time? Yes, sir. So I told you to do it yesterday. Because it will take time.
So let us start. So today we will be doing simple pipe flow simulation using Ansys. So first let us discuss about the motivation of doing this. Like this is a physiology course, but we are doing pipe flow simulation. So let us just look how it is relevant to our physiological system. So in the left hand side you can see the aorta and the coronary arteries. So and you can also see the left anterior descending artery, which is the main interest of our today's simulation. So the diameter of the left anterior descending artery is around 3.4 millimeter, and the mean flow rate in these arteries range from 66 milliliter per minute to 220 milliliter per minute. The 66 milliliter per minute is for the case when the human is at rest, like he is doing nothing, and when he is doing exercise then the flow rate is 220 milliliter. It goes up to 220 milliliter and it can be further beyond that. So the Reynolds number is typically around 600 to 1200 in that order. So we can use laminar flow instead of turbulent flow in our simulations. So the first we will be starting with the steady state simulation, where we will be prescribing an inlet velocity and an outlet pressure, and then we will move on to the pulsatile simulation. Like this is the flow through the in the right hand side the graph shows the flow through the LED. So it is pulsatile in nature. So first we will do the steady state simulation, then we will go ahead with the pulsatile simulation. And so first we will doing the Newtonian fluid, where the density and viscosity we will give the property of the blood. Like density we will give 1060 kg per meter cube and viscosity as 0.004 meter per second. But later on Newtonian we cannot use a Newtonian fluid model for blood because of its non-Newtonian rheology. So then we will demonstrate the power law and the Carreau model using Ansys. So this is the motivation behind the today's simulation. So first let us create the geometry. No, I used it in the simulation. I think just let me disconnect this and check once.
Or you can only use any computer who are going to install it.
দেখো তো কানেক্ট করে একবার। Ansys কিরকম এরকম মজা হচ্ছে না। এই যে এই অপশনগুলো আসছে না কেন হঠাৎ করে? কিন্তু আমি তো এটা তো সিমুলেশন আগে রান করিয়েছি। ঠিক আছে, এটা দিয়ে করে নিচ্ছি।
আসছে
লাইসেন্সের কিছু করলেই হবে।
তো ইনস্টিটিউট সিআইসি থেকে ও ওয়াইফাই কানেক্ট নেই বলে কি? তাহলে তো লাগবে না তোমারটা। স্যার হয়ে যাবে।
হ্যাঁ নো ডিস্টার্ব। What happened? Take this up.
সরিন sorry for the interruption. Actually, I was not connected to Institute Wi-Fi, and since I am using a licensed version, I had to connect it with the Institute Wi-Fi. So first, right click on the geometry and then open new design modeler geometry. So you can also use space claim geometry and new design modeler. So I generally use design modeler geometry instead of space claim. Yes. So just select one of the plane, any one of the plane you can select, xy plane, zx plane or the yz plane, and go to sketching. Beside the modeling we have the sketching. So from here you can click, so we want to create a cylinder of having a diameter 3.4 millimeter, of length 34 millimeter. So for first creating a cylinder, we will have to create a circle of diameter 3.4 mm. So I will just click on the circle and take the cursor to the center and draw it. So now we do not know the dimension of this circle, so we will have to give the dimensions. Like I will go click on dimension and then yes. So here we can see it's D1. I don't know whether it is visible or not. So here it is D1. So currently D1 is 16.303 meter, which is very large. So I will have to prescribe it 3.4 millimeter, which is the standard diameter of the LED. So it can vary depending based on the patient, but normally it's around 3.4 millimeter. Yes. So next we will have to extrude this circle in order to create the cylinder. So I will click on extrude and click on apply over here. And I will have to prescribe a depth which I will give as 3.4 millimeter. The depth will be around 0.34 millimeter, that is 10 times, means the length of the channel is around 10 times of the diameter. I will be taking it as 10D. So it's around 34 millimeter. So next I will click on generate. Yes, so this is the pipe like the channel in which we will be doing the simulation. So next I will close this design modeler. Next we will move towards meshing, like we will right click mesh and click on edit. So first we will go ahead prescribing the element size. So for starting I am prescribing the element size to be 0.001 meter, that is 1 millimeter element size. So let's look how the mesh looks like. So we will click on generate.
Just 1 second. Yeah, so here you can see this geometry is actually solid. You see the whole, it is not hollow. Okay, so when if you use the CAD geometry, please don't make it a shell, make it all solid. And then solid will be converted into fluid. So he is doing meshing now, and the solid part will be converted to the fluid. And the surface, okay, that is the boundary, it will be like zero thickness surface. Okay, so this is the main thing. Otherwise, I found some students, they make it hollow to make the computational domain. Don't make it hollow, make solid. Okay.
So the mesh size is pretty large, so we will have to reduce the mesh size to get accurate result. So for that we will have to right click on mesh, then insert, then we will have to click on sizing. Then we will have to select the entire body, like for the entire body I want finer mesh. So then I will click on apply, and here we will have to prescribe the element size. So I am prescribing it as 0.0002. So you can play around with the mesh size and normally for CFD simulation we do grid independence test, that is we decrease the mesh size and there comes a situation when there is no change in the result on further decreasing the mesh size. So I will click on generate. So now we have got much more finer mesh than the previous case, but you can see that the mesh in the wall is same as the, means if you see this cross section, that the size of the mesh towards the wall is still coarse, and in the towards the wall we need more finer mesh in order to capture the accurate value of wall shear stress and other parameters. So in the wall there should be much more finer mesh. So we will create inflation layer, like we will right click on mesh, insert, and then click on inflation. So here we will have to select the boundary. So the boundary is actually the wall. So here the geometry, for the geometry we will have to select the entire body. So after selecting the entire body, I will click on apply, and for this boundary I will have to select only the walls, like towards the wall we need much more finer mesh, and then I will click on apply. So here you will have to prescribe the number of layers, like till how many layers towards the wall the mesh will be finer. So by default it is 5, so I am giving it as 6. And growth rate is, suppose towards the wall the mesh size is 1 millimeter, then just away from the wall the mesh size will be 1 into 1.2. So that is the growth rate, means how the mesh size is increasing as we are moving towards the center. So that I am keeping it as default, and then I will again click on generate. So it is taking, it will take us some bit of more time. Yes, so now you can see that towards the wall, like in this cross section if you see, like we have finer mesh in the wall, towards the wall, and it is the mesh size is gradually increasing, and you can see the number of layers, like this is sorry. So you can see the count the number of layers 1, 2, 3, 4, 5, 6, like and the growth rate is 1.2, means the mesh size adjacent to the wall as we are moving it is increasing 1.2 times. So now we will have to name the faces, like which one is the inlet, which one is the outlet. So for that I will click on this each of the faces. So I will click on this, right click, and create named selection. So it is just a name, you can give any name. So this I will be using as inlet, so I am giving it the name as inlet, and the other end I am naming it as outlet. So similar procedure, right click, create named selection, and outlet. So you may or may not name the walls, so it depends upon your choice, but here we are naming it. So click on the curved surface, right click, create named selection, and name it as walls. So the meshing is done. Now we will move towards the setup. So like beside geometry you can see a green tick, but beside mesh it's an yellow update sign. So just right click on mesh and click on update. So, you can see the progress by clicking on the right bottom like this show progress button. So, you can see the progress. So, as the mesh is fine, it is taking, so yes, it is completed. So, now double click on setup. And please check this double precision sign and then click on start. So, in this setup we will be prescribing the density and viscosity of the fluid. We will be prescribing the inlet velocity and outlet boundary condition. For the outlet we will be using 0 gauge pressure boundary condition, and also which model to use, like laminar or turbulent flow model. So, first let us look at the model. So, you can select viscous laminar. So, I have seen in some of the Ansys version by default it is SST K omega by default it is SST K omega maybe. So, you can change this to laminar because our Reynolds number is between 600 to 1200. So, that is fall in the laminar region. So, please select laminar from this. And first we will be doing the steady state simulation, like we will be prescribing a mean flow rate at the inlet. So, actually the flow rate is not varying with respect to time. So, here I will set this as by default steady. For the transient simulation, we will have to click this transient. Next, we will have to choose the material. So, by default, you will find that this is air. So, you can just rename it and change the density and viscosity. So, prescribe the density as 1060 kg per meter cube and the viscosity as 0.004. So, for Newtonian fluid, when blood is assumed to be Newtonian, then we generally prescribe this density and viscosity. But again it depends upon the hematocrit percentage, which we will come later while doing the non-Newtonian models. So, just change it to 1060 and 0.004 and then click on change or create. Then you can close this. So, next comes the boundary condition. So, here we have the inlet, outlet and wall. So, just double click on inlet. Yes. So, prescribe velocity. So, our flow rate is 66 milliliter per minute, and if we divide it by the area, like the cross sectional area pi r square, then the velocity comes out to be around 0.12 meter per second. So, here prescribe the velocity to be 0.12 meter per second and then click on apply and then close. So, at outlet the gauge pressure is 0. So, this pressure boundary condition is not important for this case, because for the fluid flow the pressure gradient is important, the absolute value of pressure is not important. But for deformable wall simulations, like which we will be doing in the subsequent tutorials, for that we need to prescribe the exact pressure value that actually is there in our blood vessels. So, you know, you may be knowing the terms like cuff systolic pressure and cuff diastolic pressure. 80 the systolic pressure is 120 millimeter Hg and the diastolic pressure is 80 millimeter Hg. It's for the normal human being who is not having any disease. So, you will have to prescribe that pressure. So, actually in real cases at the inlet we also have pulsatile, we will have to prescribe pulsatile flow F1, and at the outlet we will have to prescribe pulsatile pressure. So, for this case, since it is a basic simulation, I am keeping this pressure to be 0. Yes. And walls, it is by default no slip boundary condition is given in Ansys, so I will keep it as it is. So next, click on methods under solutions. So from here you will have to select the scheme, like there are a couple of schemes like simple, simple C, PISO and coupled algorithm. So since simple algorithm has been taught to you in the previous lectures, I am using the simple algorithm for the simulation. Next, expand these monitors and double click on a residual. So here prescribe the convergence criteria to be that the absolute criteria to be 10 to the power minus 6. So by default in Ansys it is given 10 to the power minus 3, but for accurate solution you need to decrease that few orders of magnitude. So prescribe that 10 to the power minus 6. Then click on initialization and initialize the simulation. So you can see that initialization over here. Then you double click on this run simulation icon, and here you will have to prescribe the number of iterations. So I have prescribed the number of iterations to be 1000, but if you see that the solution is not converged till 1000 iteration, then you will have to increase the number of iterations. So and then click on calculate. So it will take few minutes, around 700 to 800 iterations it will take to converge. So I already have the converged solution, so I am showing it to you and showing the post processing part. So you can try this in your laptop, because as it will take around 10-15 minutes of time, I am skipping the solution. I have already, with the same boundary condition, with the same everything set up, I have the results. So I am just showing the post processing so that you can post process the simulations. So after your solution is converged, double click on these results. So I am just deleting all these things, so I am for showing it to you. So after you open the results, your screen will look like this. Then put tick mark on this inlet, outlet and the walls, then the channel will be visible to you. Then click on this contour. Then click this in this 3 dot, click on the beside the locations, click on these 3 dots and press Ctrl and select all inlet, outlet and the walls. Press all, select all these. and then click on apply. So you can increase the number of contours, like by default in Ansys it is given 11, so I am increasing it to maybe 20. So this is the way you can visualize the pressure. And for visualizing the velocity, like if I click instead of pressure, if I click on velocity, and then if I click on apply, you can see that it's 0 velocity, because we have already prescribed no slip boundary condition at the wall. So for that we will have to slice the geometry at certain locations. So here just click on location and click on plane, and then set the distance like it is around .
The XY plane or ZY plane?
No, it will be around XY plane only.
Unselect others. Contours, unselect the contours.
Okay, okay.
Yeah.
Yes, so this is the center line plane. So you can visualize the velocity in the mid plane. So for that, again click on contour. Then from here you select plane 1 and then enter and select the velocity. So this is the velocity at the mid plane. So I have cross sectioned it in that direction, but you can also get if you cross section it in other direction, then you can get the circular cross sections. Like if I may apply. Yes, so you can visualize the velocity at any, like you can play with the planes like xy plane, yz plane, zx plane. So by this you can visualize the velocity. And also in similar way you can visualize the wall shear stress, like here you have the option of density, mass flux, pressure, velocity in the 3 directions, and the wall shear stress. So you can visualize wall shear stress similar to that of pressure. So this was the first demonstration. So how many of you have Ansys installed in your laptops? Okay, so you can share among yourselves, those who do not have Ansys installed in their laptops. And you can try with the, like today I shared with you the geometry, the bifurcating channel geometry. So with similar boundary condition, similar setup, you can do the simulation for the branched channel. So this is your task right now. Okay. So you can share it with anyone, like 3 students can share one laptop, so you can
old version you can open in the latest, but the latest version you cannot open in the old version. It should.
Like you can change your places so that every 3 persons have one laptop.
Here you are drawing, but the workbench you can upload the geometry. Geometry. Import. Right click import. Import from file.
So those who have missed any of the points, they can see the live lecture and do the simulation. Like I might be too fast. Yes. So I've already shared with you the geometry. So you can just do one thing, like you do not have to create the geometry. Just right click on this geometry and import. So instead of replace, you may have import geometry, and then you can import the geometry. You can directly import the geometry. You will not have to create the geometry on your own. You can start with the meshing. And as I moved a bit fast, you can go through the live lecture. It's already there. So seeing that, you can do. Yes. So there is a step file shared in your mail.
For the geometry, you don't need the left side. You don't need, just let me go on. You want to go back to the previous side?
So I have So basically do the first question. Yes, so basically do the first question. Like I shared with you the bifurcating channel geometry. So it's same as that. So if you have missed, you can see the recorded video. It's already there. Yes, so I'm writing the density and viscosity. So the density and viscosity is also given. So you can it is not mandatory to use the inlet velocity as 0.12 meter per second. You can play it with that. So you can increase up to 0.2425. So just do it. So for the bifurcating channel, normally at the bifurcating region, the wall shear stress is expected to be higher. So just check whether through your simulation it is coming that only. Because of there is sudden change in the geometry and change in the curvature, the wall shear stress is expected to be higher in the bifurcating region. So just check that. So for doing this simulation, you can take the convergence criteria to be that. So for the time being, you can take it to be 10 to the power minus 3, because if you take 10 to the power minus 6, it is taking longer time. So it's just for the practice session. You will not get that accurate result, but yes, you can visualize the something which qualitatively will be correct, but quantitatively will not be that accurate. So yes. Sir, USB মানে pen drive. Yes, so some of you were asking about how to create plane like for velocity visualization. Some were asking. So I am just showing it once again. Like first click on this location and then click on plane. After clicking on location, click on plane. So you can give any name, so I am keeping it plane 1. So from here you can choose XY plane. So there are 3 options: XY, ZX and YZ. So first let me create the XY plane, and XY plane. Yes, and Z is the how far from the origin the plane is lying. So the total length of the channel was 34 millimeter. So I want to create a plane in the middle. So that will be around 17 millimeter. So it is in meter. So I will give. So here I have prescribed 17 millimeter. So that I create a cross section at the middle of the channel, and then click on enter. Click on apply. So you can see, so one circle is for the inlet, other circle is for the outlet, and in middle we have created a plane. So you can change the distance from the center. Like if you want the plane to be at exactly at the middle, then you give it like d by 2, L by 2. But if you want it towards the end or towards the front, then you can play with that distance. So here I prescribed Z to be 17 millimeter. So next click on contour. So this is the contour at the top you can find. So this is contour 1. So from here, like locations, beside locations you have 3 dots. Just click on the 3 dots and choose plane 1 from there and click on enter. Okay, and from this, by default it is pressure, the variable. Change the variable name to velocity and then click on apply. So you can visualize the velocity at this plane. So in similar way you can create plane in other directions also, like if I double click on plane 1 and then choose YZ plane, like I want to see now at the mid plane, and distance I will give as d by 2. So d was 34 millimeter. So this I am giving as d was 3.4 millimeter. So I am giving the distance to be 1.7 millimeter and then click on apply. Like instead of YZ plane, select ZX plane, then you can find. Yes, so this is the like velocity at the mid plane. So this is how you create the planes, and there you can see the velocity. Any other doubt like which you want to show me again? Any other? Yes. So while doing that inflation for the branched structure, the wall you can't select the wall as a whole. So just select one of the faces and then press the control key and select the other walls. So you can do multiple selection. Just press the hold the control key and that. So those who have not yet installed Ansys, so you can just talk to your friends and install it from them. So those who have already have the installed version.
quantitative data কিভাবে এক্সট্রাক্ট করতে জানো সেফলি পোস্টে অ্যালং এ লাইন একটা প্রোফাইল ভেলোসিটি প্রোফাইল যে প্যারাবোলিক ওটাকে দেখা দিতে পারে জাস্ট একটা লাইন ড্র করো মিডিল করো ঠিক লাইন ড্র করো দ্যাট ইজ দ্য কোয়ান্টিটেটিভ দিস ইজ দ্য কোয়ালিটেটিভ That doesn't matter. You do it and see whether you can do it or not. You just keep doing, just updating and just do it in console. See, not working for her. That's why I told her. Okay, do the console. Do the console. It is a different technique, but it's okay. At least you know how to do the simulation. Other info you can do it here. Ansys itself, because he did the meshing inside Ansys. But not in here. But in Ansys. It's I see it. No, I don't. But it's a pipe flow, so she can do that very good. Also, this is volume, finding volume. So in this one it is not very good. mesh is not easy to use or connect.
I also had the same problem. It is importing. If I am excluding the problem, if I am only taking only the part which has the larger measurements instead of the area where you actually use the simulations, then it is not right. When I took the larger measurements, I mean I cut the model and I tried it and it was it is really good. It is because of you have to like deviation.
We cannot show it here because it's complex.
So some has asked regarding what is the dimension for that bifurcating channel. So the bifurcating channel, if I draw it in 2D, it's something like this. So here the diameter is same as that what we have taken for the straight channel case, 3.4 millimeter. So if I name this as D0 and these two as D1, these two are I have taken to be as same diameter. It's a symmetric case. You can do the axisymmetric case and play it with that. So for the idealized geometry, we normally consider Moore's law. So basically D0 cube is equal to D1 cube plus D1 cube. Like the flow rate at the mother channel, the diameter cube of the diameter at the mother channel will be equal to the cube of the diameter of the daughter channels. So this law is known as Moore's law. So for the idealized case, we normally use this Moore's law, and for the patient specific case you can get it from medical image, the exact geometry. Yes, till now we have visualized our results qualitatively, but for quantitative visualization, first we will have to create one line, and suppose we plot any of the parameters along that line. Here we have plotted the velocity. So, for creating a line, just click on location and click on line. So, I have already created that line. So, here you can prescribe the x, y and z coordinates in order to create this line. So, So, basically this is the yellow line that has been created. So, along this yellow line I want to plot the velocity. So, you can go to this chart option in the top, then click on that chart, then click on OK. So, go to data series, and here from location you can find the location over here. From here you select line 1, the line which you have created. And from the y axis select the variable like
X axis make the velocity, and then it will show like that.
okay. So, x axis I am doing the velocity and y axis
Y.
okay, let it be.
Y is the Z or
Okay, let's see how it goes.
Y is something Z? Yes.
Yes. So, we will get a parabolic velocity profile. So, you can see that this is not exactly parabolic. So, this is because of the mesh size, we will have to make the mesh more finer, and also the convergence criteria we will have to decrease. So, to get a proper parabolic velocity profile, but from here you can give a feel of how the velocity profile will look like. So, it is 0 at the walls and it is maximum towards the center. It is basically the Hagen-Poiseuille flow which you learn in standard fluid mechanics course. So, till now what we have done is that we have done Newtonian, we have assumed the blood to be as Newtonian, but in reality it is not Newtonian. So, for non-Newtonian you can use either the power law model or the Carreau model, and there are a couple of other models also. So, what is the power law model? Basically the apparent viscosity is K, yes, K into shear rate to the power n minus 1, where the K and n, the values of K and n depends upon the hematocrit percentage. So, K is equal to C1 e to the power C2 into H means the hematocrit percentage. So, for a normal human being the hematocrit percentage is around 45%, and for anemic patient it is less, like 20 to 30%, and it can be even more. And this n is equal to, I have not written here, I forgot to write the equation, n equal to 1 minus C3 H, where this H is in terms of percentage, like H is equal to 45 for normal human being. So, either you can use this power law model or the Carreau model in Ansys. So, the Carreau model you can find the values of coefficient for 3 different hematocrits, 25%, 45% and 65%. I think it is not clearly visible, but yes, you can get this from any literature, like they have the standard coefficient values. Now, how to prescribe this power law model and Carreau model in Ansys? So, it is just a simple step, I am just showing to you. Yes. So, like in materials, you have changed the density and viscosity previously. You have changed only the density and viscosity, but here from the viscosity, instead of constant you can select this non-Newtonian power law, you can choose this option. So, if you choose this option, they will ask you to give the value of the consistency index K and power law n. So, you can calculate the value of consistency index K and the power law index n based on the hematocrit percentage using these equations. So, I am writing it over here that so, n equal to 1 minus C3 into H and K is equal to C1 into e to the power C2 into H. So, the values of C1, C2 and C3 are given. So, you can just vary the hematocrit and you can vary the K and N values by varying the hematocrit and check how the simulation results are affecting with change in hematocrit percentage. So, this is for the power law model, like you will have to prescribe the value of the consistency index and the power law index. So, you can also choose from here the Carreau model. So, here you will have to give 4 inputs, the time constant, power law index, 0 shear viscosity and infinite shear viscosity. So, all these values you can get from this table, like n naught is the 0 shear viscosity, lambda is this time constant, n is the power law index and n infinity is infinity shear viscosity. So, you can just play with these parameters and check the dependence of hematocrit on the simulation outcomes. So, this is your home task, like you can do it for straight channel. You just take the hematocrit values to be 25%, 45% and 65% and check how the simulation result is affecting. You can choose either of the power law model or the Carreau model, any one you can choose. Yes, yes. So, I am editing this part only. So, I am doing it for 45% case. So, the 0 shear viscosity is 1.610. The infinite shear viscosity is 0.0345. The power law index is 0.479. So, I am doing it for the 75% hematocrit value, and the time constant is 39.418. click on OK and then click on change or create and then click on close. So rest all the other things will be exactly the same what we have done for the Newtonian cases. It's same 0.12 meter per second. So you no, this is just I am showing how to prescribe the non-Newtonian rheology. So pulsatile flow I will be, so today there is no time, so I will show it in next class. So it's same like you can just initialize the solution and then proceed to towards the calculation. So basically I have shown this so that you can play with the hematocrit percentage and see how the simulation results are affecting with the hematocrit percentage. So those who are not familiar, hematocrit percentage is the percentage volume of red blood cells in our blood. So our blood consists of red blood cells, white blood cells and plasma. So the hematocrit percentage is the ratio of RBCs in the whole blood. So those who are not familiar with the term, for them.
understand. I did not. I did it from the early version. 3.5. Right? Version I did not do it, but you can try. You can try to connect to one and see how.
Like separately layers and
I will see. Otherwise, I cannot take it directly. I think they are not. That we not so sure because you cannot make it honest. I think it will span through this one. Just so do it, select this one and do it and see how it goes.
Faces are not sufficiently clear.
Somehow surfaces cannot be selected.
Here we are able to select the surface.
Yeah.
But after that, I used to ask me for the I can offer it.
Yeah, it is not exactly the same. You have to take different. Not exactly the same. I was telling
That
you.
is because laser difference is this is very different. That is it. That's the reason I came to India.
Yeah, tonight just try to fix your answer. You already fix it? Try to fix it just tomorrow. We work for the lab as well. We'll use the same.
I tried to fix my adding primarily adding some
It makes problem. What is this? Student version you have used or that version? But once it makes trouble, it travels a lot. That's a problem. Or you can talk to some IT expert.
Yesterday's MATLAB code is not working. Yes. Yes, yes. Okay, okay. So, some of you were facing some problem with the CFD post, but from the solution also you can get the results. Like if you click on this graphics, if you expand this graphics and double click on contour, like instead of doing it in the CFD post, you can also visualize it over here. So, suppose I want to visualize the pressure. So, it's by default it is pressure and static pressure is selected. So, just click on save or display. So, the pressure it will display the pressure contour over here. You can visualize the pressure contour. Similarly, if you select the wall fluxes, so you can plot the wall shear stress. So, those who are this is only for those who are facing problem with the CFD post, that results tab, some were facing problem. So, for them they can post process it using this solution tab which is there in CFD Fluent.
with our loss in it.